So that being said, we're now ready to classify the remainder of our phase planes. So we've already described the first three here. We already created a division here saying if we have lambdas that are real, we're going to be contained to or confined to these top three scenarios. So as I like to call this, instead of an unstable node, I like to call this a source, because all of the solutions are sourcing away from the equilibrium. This was when both eigenvalues were positive. So real numbers. Here we had all of the solutions going in towards the origin, so this we call a sink, and this is where both lambdas, lambda 1 and lambda 2, are less than 0. Then the third case, where 1 is positive, 1 is negative, we get what looks like a saddle, so a saddle point. So this, we do stick with the word saddle, and this is where one of the lambdas, doesn't matter which one, I'm just arbitrarily writing it as lambda 1 bigger than 0, lambda 2 less than 0. Now, the last three cases are complex. So these are all complex. If we had a g value of 0, and it all depends on the g value. The h value isn't going to control the behavior, it's going to control the speed with which that curve oscillates. So if this were cosine 10t, it would still, all three of these scenarios would persist, but with 10t we just have more compressed oscillations because the frequency would be 25% higher in that case. Now if g is 0, both x and y are just oscillating. They are never getting closer to the origin, they are just oscillating around the origin, the point 0, 0, and so we get what's called a center. And this is where, when you have, so complex eigenvalues, we said lambda equals g plus or minus hi. So this is when, right here, g is equal to 0. Now think about what that means. This just means no exponential amplitude. Took me a second there. Now, here we have solutions. You can see the arrows point away from the origin. By the way, none of these have straight line solutions because they don't have real eigenvectors. In the first three cases, the reason we had these straight line solutions was because we had real eigenvectors. Here in the real plane, you cannot visualize imaginary eigenvectors, and so we end up getting this behavior like spirals. So this is called, I like to call this a spiral source instead of an unstable spiral, because all of the solutions spiral away from the origin, and it matches our nomenclature from above for just the regular source. And this is going to happen whenever that g value is bigger than 0, because notice that the oscillations get bigger and bigger and bigger. And this is called, I like to call this a spiral sink. Again, similar idea here. All the solutions are moving inward. They're getting closer. They're oscillating around the origin, but they're sinking into it. And this is when g is less than 0. So you can now sketch the phase plane just by knowing the eigenvalues. And when you get a complex eigenvalue, you can completely ignore the eigenvector when you're trying to sketch the phase plane. Pretty cool. So where do we realistically see complex eigenvalues? Well, the most obvious case will be the damped spring mass system, where the oscillations stop or progressively stop because of resistance, some sort of friction, wind, air resistance, gravity, etc. What's often desirable is to decompose this system. This is called a decomposition because we are going to break this up into two first-order differential equations, in fact, a system. In order to do this, there's a little, not actually even call it a trick, but it kind of is a trick the first time you see it. We're going to create a new dependent variable called v, and we're going to assign it dy dt. So basically all we did was we just assigned the velocity of the spring mass system to a variable called v. Let v equal dy dt be a new differential equation that simply represents velocity. Now, if we let this substitution take place, if we take the derivative of both sides of this equation, The derivative of velocity is the derivative of velocity, right? So the derivative of velocity, dv dt, is the derivative of dy dt, which is the second derivative of y with respect to t. So basically that just means that change in velocity is acceleration. And now what we can do is we can substitute into our original equation. So what we're going to do is we're going to replace the second derivative with dv dt. That's based on this. And the reason we did that is because now we have the blue v equals dy dt and this equation are both now first order. They are a system because they do depend on each other. You can see that this guy now depends on v, and this guy depends on v as well. This guy depends on both v and y. The other thing that we're going to do is then we're going to substitute dy dt. We're going to replace that with v because that's the substitution we initially made. And if what I do is I isolate dv dt by moving it to the other side, then if I subtract away everything but dv dt, my first derivative, then I'll have minus k over my minus b over mv. And now I have two equations. I have dv dt, which is the change in my velocity, which is basically an acceleration equation. So acceleration equals, and then I have a velocity equation, dy dt equals v. So to put that into more of a matrix looking form, dy dt is really 0y plus 1v, and dv dt is negative spring constant divided by mass times y minus damping coefficient over m times v. And this decomposition is always the same. This never changes, so you don't really have to rederive this, but it is possible to take a second order equation and break it up into two first order equations. So that means that in general, for a spring mass system, this is going to be the matrix. Again, remember that the thing to point out here is that this is the velocity equation. If we solve it, it solves for y. This is the acceleration equation. And if we solve it, it solves for v. All I mean by that is that's the variable that we would get y equals and v equals if we solve these two equations.